Okay, finally problem 5. The last problem is this roller coaster. And I can just draw this freehand, I hope. Even I can't screw that up. So, and there's a loop that has a radius of r, preceded by a hill with a height of h. Okay, so what we need to know here is what is the maximum radius of the roller coaster loop, given that we have a hill height h. So there's this car coming off here, and it's stated in the problem. This is going to be state 1. At state 1, you know your potential energy from gravity is mgh, and we told you that basically it sort of has a negligible speed as it comes over the hill. So kinetic energy there is 0. It goes down, and then it gets going faster, and then it swirls around this loop. Now, the question is, how fast does it need to be going at the top of the loop? And this is a little sneaky. I should have said in the problem that we were sort of assuming the roller coaster car, had no way to grip the tracks, so it needs to be going fast enough that it's not going to fall off. This is like one of those problems from the last unit, where if you do a free body diagram of this car as it's sort of going around the loop this way, okay? So I'm not sure why I drew that arrow there, but it's going around the loop this way, counterclockwise. If you do a free body diagram of it when it's at the top, okay, the forces acting on it are a normal force and its weight, okay? So the normal force, and if you look at these two together, normal force, if it's accelerating this way, so we say, let me say, like this is the positive y direction, okay? So what we say if we do a sum of forces in the y direction is that, let me do that down there, normal force plus mg equals ma, and that a has to be equal to v squared over r because it's going in this circular motion here. So you look at this and you say, plug all these in, and what you get is normal plus mg equals m v squared over r. Okay, because it's going in this circular motion right here. It needs some acceleration downwards. So the sort of the slowest it can be going, or the case right before it falls off, right before it it loses contact here, is where the normal force is 0. So let's say the normal force is not there, and that'll give us sort of the lowest possible v that we can have and have this work. So in that case, then what we get is v squared equals rg. And what this represents is the slowest possible speed it can be going at the top here if it's not going to fall off the tracks. Anything less than that, and it's going too slow, and it sort of comes up the loop, it goes woo, and then falls like that. Okay. And everybody screams and dies. Okay, so at state 2, the potential energy then, and I should have said, by the way, for 1, I'm measuring potential energy relative to potential energy due to gravity is 0 right here. Okay, so at state 2 now you are r up and then another r up. So your total potential energy from gravity is 2 mgr, and your kinetic energy is 1/2 mv squared, and your v had better be this. So let me do that and say your kinetic energy then, if you're going the absolute slowest you can go, is k equals 1/2 mrg. Okay, or you can rearrange it and be mgr, and so it's the same as this. So what we get is if we do Emec at 1 equals Emec at 2, then we get, on the 1, we get mgh equals 2 mgr, this is the potential energy here, and then the kinetic energy plus 1/2 mgr. That's this kinetic energy here. So you get mgh equals 5/2 mgr, which means the biggest possible loop you can have is r equals 2/5 h. And there you go. That is all the review problems. Hope that helped.